In this video, we're going to talk about aldol addition and condensation reactions. The aldol condensation refers to the reaction between two carbonyl partners and involve a combination of nucleophilic addition and alpha substitution steps, as we're going to see. So first, let's look at the reaction of a general aldehyde shown below using a base. And so this is called a base-catalyzed aldol addition. The hydroxide ion is going to act as a base, meaning that it's going to deprotonate an acidic hydrogen. So just take a few seconds and see if you can identify acidic hydrogens in this aldehyde. So remember, we called the carbon next to the carbonyl group an alpha carbon, and the hydrogens on that carbon are also called alpha hydrogens. And we know these alpha hydrogens are acidic because the conjugate base is stabilized through resonance. So the hydroxide is going to grab that hydrogen, and we're going to get this conjugate base like this, and a double bond right here. Now this is called an enolate, and this is stabilized through resonance because I can draw another form where the negative charge is on carbon. Like this. And in this form, this is actually a nucleophile, and this is what's going to be involved in the aldol addition and condensation. Now we also generate water as a byproduct because OH plus hydrogen gives us the water. Okay, so let's go to the second step. So the first step involves the formation of enolate, and this is our nucleophile. Now where's our electrophile, or the electrophilic center? So the electrophilic center is the carbonyl carbon. Remember, this has a partial positive charge, meaning that the nucleophile is going to attack there. So we form this double bond, and this will attack here. We can't have 5 bonds, so we're going to break that pi bond, and this gives us this intermediate right here. So one trick if you want to use for making sure you've drawn the correct product is to just count the number of carbons. So the green one, we have 1, 2, 3, 1, 2, 3. And for the black one, we have 1, 2, 3. Here we have 1, 2, 3. So in an aldol addition reaction, the number of carbons in the product is just the sum of the carbons of the starting material. So 3 plus 3, 6. So our product has 6 carbons. Now in the first step, remember, we formed water. So in the last step, we're just going to protonate this oxygen using the hydrogen in water, and this gives us this product right here. And this is all often referred to as aldol product. And it's actually a beta hydroxy aldehyde. So it's called beta hydroxy because, again, remember, this is the alpha carbon right next to the carbonyl group. The carbon after that is called the beta, and on the beta carbon we have a hydroxy, so this is called a beta hydroxy aldehyde. Now if we had started with a ketone, so if instead of aldehyde we had a ketone, then the product would have just been a beta hydroxy ketone. So you can do the same reaction, aldol addition, with a ketone. Now in this step, when the oxygen grabs this hydrogen, we'll form our hydroxy. So this is truly a base-catalyzed reaction because the hydroxy is being regenerated. And lastly, This aldehyde, the enolate of the aldehyde reacted with the same aldehyde. So the aldehyde reacted with itself, and this is called a self-aldol addition. So now the reaction usually doesn't stop at beta hydroxyaldehyde. So we go one step further, and this is called base-catalyzed aldol condensation. So the first step is addition, and then we have the condensation reaction. So again, it's the same reaction. So we have hydroxide ion floating around, and this is going to grab this hydrogen right here, formed a double bond here, and this is going to be our intermediate right here. Now we know that OH groups are usually bad leaving groups. You have to first make them to a good leaving group by protonating them, so OH2 plus, and then they can leave as water. So in general, they're bad leaving group. But here, because we have this carbonyl group right here, it actually helps to kick out that OH group. So we form the double bond here, and this kicks this OH group out. And this is through the E1CB elimination. So make sure you review that if you're not entirely sure what that is. Okay, and now this gives us the final product, which is alpha beta unsaturated carbonyl. So again, this is called alpha beta because this is the alpha carbon, this is the beta, we have a double bond, so this is unsaturated. Okay, so we talked about the base-catalyzed aldol addition, base-catalyzed aldol condensation. Now, the reaction here, the addition reaction, you can see all these equilibrium arrows, meaning that these steps are reversible. So this is called the retro-aldol reaction, where we take the addition product and we go the other way around to give us the original aldehydes. So let's talk about the mechanism. So again, we can use the base, and this base is going to grab that hydrogen. We make a double bond here, double bond, and we break this double bond right here, and this gives us the aldehyde, original aldehyde, and this is the enolate version of the aldehyde. So in the second step, you can technically use acid to protonate this, which then gives you the original aldehyde. So again, the aldol addition reaction is in equilibrium, and it can go in the reverse reactions. It's called the retro-aldol reaction, and this gives us the original aldehyde plus the enolate of that aldehyde, or if we had used the ketone and the enolate of that ketone. So now let's look at the acid-catalyzed aldol addition. We talked about the base-catalyzed, but now let's talk about the acid-catalyzed. So we're going to talk about using ketone in this case. So you can see that the reaction is can be done using ketone as well. Because we're under acidic condition, the oxygen gets protonated, and this forms the enol. Now, enols are usually less nucleophilic than enolates, but the reaction happens because this oxygen is protonated, and we know that once we protonate this oxygen, it becomes positively charged, and now this carbon is even more electrophilic because it even has more partial positive charges on it. So the electrons on the oxygen make a double bond, and this attacks our electrophilic center. We break that bond right here, and this is the intermediate that we get. Again, you can count the number of carbons to make sure we drew the reaction right, so, or the product right. 1 2 3, 1 2 3 for the green one, and then 1 2 3, 1 2 3 for the black one. So 3 plus 3, 6. We need 6 carbons in our product. Now in the last step, we're just going to deprotonate that oxygen because it's positively charged, not really happy. So once we deprotonate that, we get our beta hydroxy ketone. And we regenerate the hydrogen. So again, this is truly an acid-catalyzed reaction. Okay, so then the reaction usually continues to aldol condensation. So now we're under acidic condition. The very first step that happens is that the OH becomes protonated, and this makes it a very good leaving group. It just leaves as water. So this leaves. We have water being generated, and this forms a positive charge right here. And in the next step, this just gets deprotonated, and we form the double bond here. So again, this is our alpha beta unsaturated carbonyl. And this step is done through an E1 elimination. So again, make sure you review it if you're not sure what that is. Okay, so let's just go back to base-catalyzed. So we said that when we do under basic conditions, we do base-catalyzed addition. The reaction usually doesn't stop there, and then we get base-catalyzed aldol condensation. So we get the elimination product. The base-catalyzed aldol reaction sometimes gives the aldol addition and sometimes the aldol condensation reaction. The choice is based on conditions. For example, the more vigorous conditions such as stronger base, higher temperatures, or longer reaction times tend to give the elimination reaction, so the unsaturated carbonyl group. It also depends on the structure of the reagent. Some combinations are easy to stop at the aldol addition, while some always give the aldol condensation. Now for acid-catalyzed addition, the condensation is easier to get compared to base-catalyzed. So usually when you're under acidic conditions, usually you will get the elimination or the unsaturated carbonyl rather than the beta hydroxy ketone or the addition product. Okay, so far we only talked about the aldol condensation and addition reactions with only one carbonyl group. But what if we have two different carbonyl partners? So this is called a mixed aldol condensation, and here we have acetophenone and benzaldehyde. So benzaldehyde is in green, acetophenone is in black. Take a few seconds and see if you can identify all the alpha hydrogens. So benzaldehyde doesn't have any alpha hydrogen. Remember, the hydrogen of aldehyde is not alpha hydrogen. The ketone has 3 hydrogens right here, and these are going to be our alpha hydrogens, and they can get deprotonated, and it can give us the enolate. Then in the second step, the enolate is going to attack the electrophilic center right here, and this gives us this intermediate right here. I skipped the protonation step, so I drew the O minus as OH, so just remember that this gets protonated, and then we can proceed to the condensation step. So this is the condensation, and this gives us the alpha beta unsaturated product. So you might ask yourself, why did this enolate attack the aldehyde and not the carbonyl or the ketone? Sorry. So why did it attack the aldehyde and not the ketone? And the answer to that is that, remember that ketones are less reactive than aldehydes. So given the choice, the enolate attacks the more reactive aldehyde than the ketone. So let's look at another example. Here we have benzophenone and propanol. Again, take a few seconds and see if you can identify all of the alpha hydrogens. So benzophenone doesn't have any alpha hydrogens. Our aldehyde has 2 hydrogens or alpha hydrogens right here. So this is going to give us the enolate. Now, will this enolate attack the aldehyde, or will it attack the ketone? So it turns out that the enolate will not attack the benzophenone. So this won't attack benzophenone. And the reason is that because this is very hindered, it has 2 phenyl groups. So 2 phenyl groups right here. So it first of all, is even less reactive than normal ketone without this much hindrance or steric around it. And then we know normal ketones are even less electrophilic than aldehyde. So actually, the enolate is going to attack the aldehyde, and it's going to be a self-aldol reaction, and the benzophenone is just going to sit around and do nothing. So the conclusion is that for cross-aldol reactions to work successfully, you need 2 criteria. First, only one partner should have enolizable hydrogen, the other one should not have enolizable hydrogen. So number 2, the other partner must be incapable of enolization and must be more electrophilic than the first partner. So this second one is sometimes easy to forget, but it's actually very important, because if that's not being satisfied, then the mixed or the cross-aldol reaction or mixed aldol reaction will give you either mixture of products or give you unwanted products. So in this case, for example, we wanted this enolate to attack the ketone, but it's not going to do that and gives us the unwanted product. So this is very important. And lastly, let's just look at unsymmetrical ketones. Here we have an unsymmetrical ketone, and that means that we have 2 types of alpha hydrogen. So we have 3 hydrogens right here, I'm going to call this A, and we have one hydrogen right here. I'm going to call this B. So if we deprotonate hydrogens A, we get the enolate here. We're going to call this enolate A, and enolate B if we deprotonate that hydrogen, or hydrogen B. Now if I use sodium hydroxide at room temperature, which enolate do you think will I get? Enolate A or enolate B? Again, using sodium hydroxide at room temperature. I'm going to get enolate B, so sodium hydroxide, room temperature, and the reason is that because, as you can see, the double bond is more substituents, and we know that the more substituents are around the double bond, the more stable they are. So this is the more stable product, and that's why we call this the thermodynamic product, because it's the more stable one. Now what if I use a very bulky base such as LDA? So this is a very bulky base, and I'll use cold temperature, so minus 78. Now in this case we're going to get enolate A, and the reason is because this is a very bulky base, it will have a harder time reaching this hydrogen compared to these hydrogen, because you can see we have two methyl groups right here. There's steric around this hydrogen, and this is already bulky. How is it going to get that hydrogen? It's very easier for this bulky base to get these hydrogens instead. And that's why this enolate, so enolate A, is going to be produced faster, and that's why we call this the kinetic product. So for unsymmetrical ketones, it depends on the reaction conditions, which enolate you're going to get, and hence which enolate is going to act as the nucleophile. So very briefly, we talked about aldol addition and condensation. We started with base-catalyzed aldol addition. The very first step is to get enolate, because the alpha hydrogens are acidic, and the second step, the enolate acts as the nucleophile to attack carbonyl groups. So this can be the same aldehyde, in that case it's going to be self-aldol, or a different carbonyl group, in that case it's going to be crossed or mixed aldol addition. The product of the addition is beta hydroxyaldehyde. Again, depending on the reaction condition, the reaction might go one step further. This gives us the condensation reaction. So the product is alpha beta unsaturated carbonyl product. The aldol addition is in equilibrium, meaning it can go in the reverse reaction. And this gives us the aldehyde, so the original aldehyde, and the enolate of the aldehyde. We also talked about acid-catalyzed aldol addition. In this case, we form enol, and the enol is going to be our nucleophile, giving us beta hydroxyketone. Under acidic conditions, it's very easier to get the condensation product, or alpha beta unsaturated carbonyl group, and this happens through even elimination. We talked about mixed aldol or crossed aldol reaction using two different carbonyl product. For these reactions to be successful, only one partner should have enolizable hydrogen. The other must be incapable of enolization and must be more electrophilic than the first partner. And lastly, for unsymmetrical ketones, it's important to know the reaction conditions to know which product is being formed, or which enolate is being formed, the thermodynamic or the kinetic enolate. Thank you for watching.